Okay. Hello, class. Hope everyone is doing well. We're getting very close to the end of semester. Today, we're going to wrap up the t-test. The last t-test that we're going to cover is independent measure t-test or two independent t-test. That's the same, two independent or just independent t-test. After this, we have one more session left, and that would be ANOVA, analysis of variance, and I'm gonna uh, go over that perhaps next week or week after that. But there's only like a couple of more weeks left. Next week is Thanksgiving. Hope you have a great Thanksgiving. And after that, your final will be due. And just check with your syllabus, and I also will let you know before the deadline, just to remind you. Once again, I hope you're happy with your midterm. If not, you should know why. For example, if you had anything less than A, it means that you did not complete the requirements, like, for example, SPSS assignments. So again, that's a very important component of this course. And again, and it's very important for you guys to know this, how to work with SPSS. And it's not too late. I still encourage you to do so. If you don't have the SPSS, all you have to do, contact the IT, Albizio IT department. They download one to your computer, and just do those SPSS assignments. Other than that, just let me know, please, if you have any question, concern, or anything. So with no further delay, we're going to cover this chapter. If you already understand single sample t-test and repeated measure t-test, you have no problem understanding this one. And like mentioned early in the past, there are three different types of t-tests, and it's all about research. single sample research, single sample t-test. We have one sample, also known as student t-test, because they conduct this kind of research in universities. Then related sample. So for the first one, you have one sample from one population. For the second one, related sample, you still have one sample from one population. The only difference is, just like the name suggests, you repeat the measurement twice. If it's more than twice, that's ANOVA. And that's the topic that we will cover next week or week after that. So tonight we're going to go over two independent sample, also known as between subject design or matched subject experiment. You don't have to say the two, so it's just independent sample, t-test. We'll do it. T-test. And just like the name suggests, independent or two independent, that means you got to have two groups or two different samples. Like you compare AU students with FIU students. Two population, two samples, two of everything. That means you're going to have two different variance, two different standard deviation, two different degrees of freedom. Degrees of freedom for sample 1, degrees of freedom for sample 2, DF. So again, your sample don't have to have equal participants. If they do, it's fine. If they don't, it's fine. For example, if you have two samples from two universities and you have 20 participants in each, the DF1 will be n-1, which is 19, 20 minus 1, and the second one will be the same, 20 minus 1, 19 and 19. But again, your total DF is when you add those two up. Yeah, that means 19 plus 19 is 38. There's another way to calculate that, and that is if you know your total participants, like 20 and 20, 40. So subtract 2 from that 40 is 38. It's the same thing. So either way will do. You can go over these slides and they very detailed, explain everything. And please, once again, let me know if you have any question, concern. So once again, you have two different samples. If there's no difference between the two samples, as you can see, two different distribution, FIU and Albizio, you would be able to see only one distribution because they are identical. The blue line, that's mean for each sample. So if they're same, then you only see one blue line. But the chances are, whatever your hypothesis is, you're saying there is a difference between the, let's say, self-esteem of AU students and FIU students. So the larger the difference, that's D, effect size. That's why we have to measure effect size. The better. The better means more power we have to reject a null. Or when we conduct research, the higher your D effect size, the more chance you have to reject a null. Null says there's no difference between your two groups. And then once again, we are working with parametric test. All these three tests, three t-tests, are parametric. And parametric tests, we said that they have assumptions, and one of them is sample size. I mean, you got to have at least 30 participants. And if you have less than 30, if you work in some place and you want to conduct research and use any of these t-tests, but you don't have enough participants, you can't use that t-test. You have to know what's the non-parametric test equivalent to this test. Like, for example, tonight at the bottom of the screen, it said instead of independent measure t-test, we're going to use u-test or Mann-Whitney rank u-test or just u-test. And then last time we talked about Wilcoxon, and then before that we talked about sign test. So that's what we're going to cover tonight, independent sample t-test, also known as between subject design, or matched subject design. That means between means, do you want to know the difference between the two groups? Between the mean of two groups. For example, again, self-esteem or self-efficacy of AU students with FIU. You have a sample of a couple of hundred of each institution, give them self-esteem, find out what's the mean. Let's say on a scale of 1 to 100, FIU self-esteem, FIU students self-esteem will be 90, and AU will be 95. So compare those two, which is the difference is 5 points. But is that significant? Does it have a statistical significance? We don't know unless we test our hypothesis. That means follow the 4 steps. Step 1, no, it says no difference. We, the researcher, alternative hypothesis says, yes, there are differences. And step 2, we got to find our critical values. And step 3, calculate our t, calculated t, which we're going to go over the formula. And if the calculated t is greater than critical value of t, then we reject the node, because the value goes into rejection zone. That's what we've been talking about. Same thing applies for all these tested statistics. And then again, the last chapter we're going to cover next time is ANOVA. And I just want to let you know that ANOVA is just another t-test. What's the difference? The difference is for t-tests, you use 1 or 2 samples. But you might just say, you might thinking right now, well, what if I wanted to compare the self-esteem of 3 or more universities? Like, what's this, compare self-esteem of students at FIU, AU, University of Miami, or even more. Then what? Then you use ANOVA, which is more complicated, more samples, means more formula. And you're going to see that difference next time. These are lined up from left to right. These lined up are different. Hold on, please. Yeah. Yeah, I'm presenting. Oh, okay. All right, I'll talk to you later. All right, sorry about that. Okay, sorry about that. So yeah, those are the formula, the red for from the left column. T is m minus mu. If you look at them, you see they all pretty much the same. For single sample, is the difference between sample mean and population mean, but in this case, it's not a population mean. It's just the mean of the previous group comparing with something divided by estimated standard error. The second one, once again, is mean difference, sample mean difference minus population mean difference, which Noel says that population mean difference is always said that value is 0. So, and divided by estimated standard error of the mean difference. And this one tonight, same thing, is the sample mean difference. We got two different mean from two different population sample mean of samples from different populations, and and null says the difference should be 0, so that on numerator where it says 0, that don't count. Divided by estimated standard error, mean difference. And you can see the green part that you got to calculate the estimated standard error, and one way or another. The formula for tonight, the new formula is that we're going to cover is called pool variance. That's a new variance. Pool variance means average variance. So let me just focus on tonight formula, which is this. So that's the formula, the red on top, two independent, and the one is circled. Difference is that's 0. That value is 0, so you don't write it down. So you got two samples, like the data on the right, which problem we're going to go over. It shows that two group of students, one watched the Sesame Street when they were kids, one didn't. And we know the mean for their, now they're in high school, and we know the mean of their exams, which is 92 for the one that who watched the Sesame Street when the 93, and 85, which is in black, is the one who didn't watch the Sesame Street when they were kids. We go over this problem so you know what I'm talking about. So anyway, we got two population, one student who watched the Sesame Street, one who didn't. And notice the difference between their mean will be 0. That means if the first group mean is 93, the second one is 93, but it's not so. Our data shows otherwise. It's 85. So that's what always null says, no difference. So with that, the numerator will be M1 minus M2, the difference between the two means, which is 93 minus 85, which is 8 points, divided by estimated standard error. And there are two ways to calculate the estimated standard error. One long way, short way, and this or the short way. The short way is using pool variance. Variance symbol is S squared. You should know by now. And again, since we have two samples, so we have two variance. Variance 1, variance 2. That's S squared 1, S squared 2. And the formula for it is SS over DF. You can use that way. This is long way. I don't recommend, but learn the new formula, which you should, which is pool variance. Pool variance, like you see right there, the last formula in green is S squared P. P stands for pooled. Pooled means average. So that means if you have one variance is 2 and the other variance is 4, the average between 2 and 4, you add them up is 6, divided by 2 is 3. So your pool variance, average variance will be 3. You can use that pool variance for both of them, for variance 1 and 2, and instead of calculating each individually. So once you calculate the pool variance, you plug it in into that estimated standard error, the square root of pool variance 1 divided by first sample size plus estimated standard error 2 divided by pool variance. And that, once you've done that, you plug it in and gives you the value for DF. for t. And df, total number, we have 20, 10 in each group, minus 2 would be 18. Or you can add a map, and we're going to go over it in a second. Once again, that's how you calculate the Collins D, M1 minus M2, M2, the difference between the two samples divided by square root of pool variance. The square root of pool variance is just like a square root of variance is standard deviation. So a square root of pool variance is pool standard deviation. Is pool standard deviation. Okay. And the last formula here, let me try to bring it up, is R squared. R squared, the same R squared we've been talking about, equals to T squared divided by the T squared plus DF. And let me see. The square root of R squared is R. R is correlation, is something we'll talk about in advanced statistics. So this is all the calculation. We're going to go over it in a second. Okay. Let me... Okay. So once again, hypothesis testing, null always says no difference, H0. Alternative or researcher would say, yes, there is, but there are differences. The difference between the two mean. Okay. And then again, that's your critical value. On page 702, critical values for t-test. You go there based on your degrees of freedom. And your alpha, you will find your critical values. And that's the t-fan. Like I said, in that formula, this formula has all the, this slide has all the formula you need. It's the same thing as this one. All the formula you need for this chapter is this, right there. We already talked about them. So again, these are individually explained. That's the t-test and estimated standard error, the detail about it. Okay, 2 ways to write it down. Either way will do. Then you can use pool variance, which is this, or this. 2 ways to do that. And once again, the square root of pool variance on the right is pool standard deviation. That's what SP is. And step 4, you make a decision. So those highlighted are critical region or rejection zone. So if our calculated T is greater than critical value, the critical values are right there when the cut points are. If it's greater, it's going to go into critical region or rejection zone, and we reject. And then again, in terms of effect size, numerator is same. The difference between the two means of two different samples, divided by either square root of pool variance or just pool standard deviation, which it is. All right, so again, that shows that the D effect size, the larger, the better, because you see that you can clearly see the difference between the two samples. But if it's small, it become identical. Like if a D is 0, that means no difference. D means 0. D means difference. So if it's 0 value, then there's no difference. R squared, once you calculate the T, You square it with df, that gives you the value of r squared, which is percentage of variance accounted for by the treatment, similar to Cohen's d, also known as omega squared. So let's go over the problem, research problem, and then let me see if we can make this a little larger. Okay. We're going to go over this research problem. We're going to go over the calculations, and then we're going to do the SPSS. So you know how it's done. It's extremely easy once you start doing it. And then we're going to go over non-parametric tests, knowing that this is a parametric test. And if you don't have enough sample size, you need to know what is statistic. What statistics is equal to independent measure t-test, which we said is u-test. Mann-Whitney u-test or just u-test? Just 1 second, please. All right. Okay. So it says research results suggest a relationship between TV viewing habit of 5-year-old children and their future performance in high school. So, for example, these researchers are saying that a student who regularly watched Sesame Street as children had better grades in high school than their peers who didn't watch Sesame Street. Well, we wanted to know if this is true. We start conducting a research. We have 20 high school students, and we asked the parents when they were 5 years old if they watched the Sesame Street or not. And 10 students in each group, 10 said yes, 10 said no, and according to the parents. And we set the alpha 0.05, we used two-tail, and here's our data. As you can see, we compared their exams. The red are the one who watched the Sesame Street, and the blacks are who didn't. And you can see that red's mean is slightly higher, 8 points to be exact, difference than the black, M1 and M2. And again, there are 10 people, N1 and N2, and SS is also calculated for each. So the question is there a significant difference between the two groups? In other words, is it really true that watching Sesame Street as a child will help you or help your child to do better in high school? We're gonna test this hypothesis, and this is all the formula we need, and this is our, again, this is our critical value. First thing first, we need to go over our hypothesis testing, and that's what we're going to do. We start with the pink dot. No says no difference. H1 alternative says there are difference. No says the difference between the two mean is same. I mean, the two mean have the same score, but that means if first one is 93, the second one is 93. 93 minus 93 is 0. We say no. The difference is not going to be 0. 93 and 85, the difference is 8 points. That's how we test our hypothesis. The step 2, we need to find the critical value. As you can see, the easiest way will be we have 20 participants, and minus 2 will be 18. 20 minus 2 is 18. And then we got to go to critical value table, and you can see right there. Let me make it larger slide. Degrees of freedom is 18, the first column, and then the second row, two tail, look at 0.05, 0.05, right there where I underline. 2.101 is our critical region starts. So you draw your distribution of t-test, which is just like z, with a mean of 0, and then a standard deviation of 1, go up positive, go down negative. With 2.101 is the cutoff point when the critical region starts, positive or negative, because it's two-tailed, either way. So that's our step 2, the red dot. Step 3, we start working on formula, which is m minus 1, m1 minus 1, m1 minus m2, the difference between the two mean, which is 93 minus 85. And then now we have to estimate the standard error. We said the best way is to calculate the pool variance. And we did. Pool variance is very easy to calculate. We already have SS1 and SS2. You can see the data on your top right side of the computer. And that is 200 and 160. And DF1 and DF2, or just DF total. DF total is 18, or DF1 is 9. That's 10 minus 1 and 10 minus 1. 9 plus 9. Either way is 18. So 360 divided by 18 is 20 is our pool variance. You plug it in the formula on top, green. And instead of, okay, see that? Pool variance, 20. And divided by 10, which is the first sample, plus pool variance, 20, divided by second sample, which is 10. That would be 2 plus 2. The square root of 4 is 2. That is our estimated standard error. And we put it right there in our formula at the denominator. So numerator is 8, denominator is 2. 4 divided by 8 divided by 2 is 4. That is our critical, that is our calculated t. Our critical value of t is 2.1. So since it's positive, you see that red dot on the right side of distribution, the bell-shaped distribution, that's where the 4 is. It's right in the rejection zone. Therefore, our decision is reject the node. In research, if this was a research group that watched the Sesame Street were known as treated group or treatment group, and the one who didn't were called control group. So you know. And again, these are the 4 steps that we talked about in detail, critical values, and last step. This is all the formula we talked about. Again, they're all in one slide. That's step 4. Same thing we talked about. So again, in reality, we don't have enough participant to do the t-test. if this was real, we would have used non-parametric test. But let's use the SPSS first for parametric test, then for non-parametric test. It's pretty much the same. They're equally the same in terms of knowing how to do it. As usual, you open your SPSS and you type in group. You go to right there at bottom left says variable views. You type in group and you type in Sesame Street. Since Sesame Street is two words, again, I wrote use underscore. You're not supposed to put the space between the words. So either no space or use underscore between the words, like I did. With that in mind, you click on at the bottom left, it says data view, and you type in all that data that I showed you. Okay. Under the group, you have two groups. Group 1, just write 10, 10, 10, 10, 10 times. 1 to 10. See, the first column is blue, and those are your participants. You can see it goes to 20. And then you have two variables, group and Sesame Street. Under the group, you write from 1 to 10, just write 1, 1, 1, 1, 1. That means all these people are in group 1. And then 2, 2, 2, 2, 10 times group 2. And those values that I showed you, you just stack them up. It's the same way that as this, the same data here. It's the same data here and here. That's your group 1 in red, group 2. Except here we have them in two columns, but we're gonna stack that watch Sesame Street group 1 on top of the didn't watch Sesame Street, or stack the red on top of the black. And then on the left you write 1 to 10. These are going to be 1, 1, 1, 1, and then 11 to 20. The black are going to be 11 all the way to 10. And those are group 2, 2, 2, 2, 2. This is how you put them in SPSS format, right there. Once you got your group and Sesame Street, right, says, okay, in the first column, in the second column, under group, you write 1, 1, 1, 1, 10 times, 2, 2, 2, 2, 10 times, and then those are the value. You type them in. Then, rest of it is piece of cake. Analyze as usual, and you use compare mean, and you look for the t-test that we're using, which is independent measure t-test. You click on it, and this is what you get. What you need to do, those two, like I said, those Sesame and group. Sesame, move it to the right where it says test value, and then move the group to the bottom one where it says group. And then you see the right there under the group says question mark. So if you click at the bottom of it, it says define group, the little table will open. SPSS asks you, what do you mean by 1 and 2? You say group 1, just write 1, group 2, write 2, continue, and then OK. And that's your output. So with that in mind, you have to be able to read this. Let me make it larger. How do we know we reject the null or not? You can see this output is two color, black and white. The white part is something that is called Levene's test of equality. SPSS would do that by default whenever you have two or more groups, and you're going to see that in ANOVA too. And as you can see, it's not significant. That's good. Unlike the null hypothesis that we have to find the significant, since that number is greater than 0.05, so it's not significant. But the t-test hypothesis is in black. And then where you're going to look for it is right here. Let me draw. I can draw something. Draw. Right here. Draw. Right there when it says significant. Right there. That's for t-test. Make it large. Okay. So did we reject the null? According to this, it says significant two-tailed test 0.001. Yes, we did. How do we know? Because 0.001 is less than alpha. How do you know what alpha is? Right there when it says not on the top right, a black table, 95% confidence interval. That tells us that alpha is 5% in metric and 0.05 in proportion. So yes, alpha is 0.05 and 0.001 is less than 0.05. We reject. But on the white part, Levene tester equality 0.5 is greater than 0.05. We fail to reject, which is good. So that's in other words, this tells us that we use the right statistic test or test the statistics. Because for Levene equality test, we should always accept the test, accept the null. And for the t-test or ANOVA, we should always reject the null. And we did. Again, by comparing those numbers with alpha. And alpha that we use is either 0.05 or 0.01. So that those numbers will clearly tell you what's going on. And the rest of it is just easy to understand. Mean, we calculate the mean was 8. And the standard deviation is all calculated. Next, we're going to go over non-parametric tests for this test. Again, non-parametrics, we talked about them, and here's more description. And the one we're going to use for repeated measure independent measure t-test is called Mann-Whitney ranked U-test or just U-test. How do we do it? We go same way. We put our data input. We go back to our input, and you can see the same data group, right? And Sesame Street. But this time we're going to use non-parametric tests. We go to Analyze. We click on non-parametric test, legacy dialog, and two independent measure t-tests. And again, same thing we just did. You transfer your group to the bottom and Sesame to top, and then you see the question mark. You click on the bottom where it says, define group, and then group 1 is 1, group 2 is 2. Click OK, and That's your, okay. That's your output. And let me make it larger. How do we know we reject the null? Again, alpha for non-parametric is always 0.05. And as you can see, it says right there, the highlighted black, it says the symptotic significant. That means it's extremely close to 0. 0.003 is less than alpha, which is 0.05. So we reject. And this one too. Okay. Go over the problems. Problems are really easy. Like I said, if you guys do them and send them to me, you will have extra point. Like again, what is the pool variance? So first, you gotta have that right here. I have printed the page that slide that contain all the formula. So what they want a pool variance. And look at pool variance is SS1 plus SS2 divided by DF1 plus DF2. And you have all that information. So SS1, and you got 2 SS and 2 N. So you need DF1 and DF2. That means N minus 1. 9 minus 1 is 8, and 6 minus 1 is 5. 8 and 5 is 13. So that would be your denominator, 13, and your numerator will be 100 plus 1500. That's 1600. 1600 divided by 13. So that's all. And then the second one, same thing. What is the variance? Pool variance, same thing. Do the same thing. Okay. And this one, it says, what's the estimated standard error for independent measure t-test? For this following, we got 2 sample, again, 2 different size, 110, 15, and 2 different SS. So you need to calculate the pool variance and then plug them into estimate the standard error, which is the square root of pool variance 1 divided by N1 plus pool variance 2 divided by 1. The next one says the data from independent measure produces sample mean difference. So the mean difference, that means the difference between M1 and M2 is 6 points. So that's 6. The numerator is 6. And your pool variance is 2. And N, if N is 2, score in each sample. So that means you have 18 people. 18 minus 2 is 16. Then estimate the standard error. So you plug in those into your formula. This one says the critical region. So all you have to do, this is 20 minus 2. Okay, so each has 20. So you got 4 people. You got 40 people. 20, one group, 21 group, that's 40. Minus 2 is 38. That's, you got to go and look for critical value, like I showed you. Column 1, DF is 38, and then you can look for first row, alpha 0.05, and two-tail. That should give you the value. And then again, this one is pretty much the same thing. Independent measure, research study uses 2 samples. Each is 9, so you got 18 participants. Your DF is 16. If the data produced T statistics, so our calculated T is 3.5, is already calculated for you. So then, which of the following make a decision basically on two-tail, 0.05 and alpha, 0.01. So one at a time, in other words, you have to find the critical value for the t-test with degrees of freedom of 16, here, number 6. And if it is less than 3.5, then if it's less than 3.5, then you reject, because calculated T is greater. But if it's greater than 3.5, then 3.5 is going to fall short. Then you have to retain the null. And then this one, the researcher report T24, it's customary to write the DF in this format. So that's the degrees of freedom for this test. And that's 410 is the calculated t-test. So degrees of freedom is 24. What does that mean? It means your n is 26, because the f plus 2 is n, 26 people for an independent measure design. How many individuals? We already said it, 26. An independent measure experiment uses 2 samples, 11 and 11, so that's 22 people. The t-statistics experiment will have the degrees of freedom of what? So again, that's 22 minus 2 is 20. They're not hard, you know. All right, so that's pretty much it. Hope you have a great Thanksgiving, and we will cover this last chapter, which is ANOVA. Please let me know if you have any question or concern. Have a great day. Bye-bye.